nature. The first is the Gauss's law, second is the nature of electric field, then the nature of magnetic field, and the Ampere's law. So when we talk about the time varying field, what happens in the time varying fields? So now we are assuming the electric field, magnetic field is varying with respect to time. So the first equation, the equation number 1 and the equation number 3, or you can say the dot equations, divergence equations, these two equations will remain unchanged. So the change will happen in the equation number 2 and the equation number 4. So this change we'll study. Okay. So let me just share the screen. Okay. So now we'll discuss about the second Maxwell equation and the fourth Maxwell equation, which needs modification, and why it needs modification. We'll see why. So the equation number. So we'll write from this time varying fields. Now we are discussing about time varying fields. So the in this only two equations will change. First we'll study Maxwell's second equation, which needs modification, and in this we will study the Faraday's law. Faraday's law. Till now we know that E dot dl is equal to 0. E is what? Electric field intensity, volt per meter. This is meter, so this is nothing but summation of volt is equal to 0, or our KVL, right? But Faraday says that voltage can be induced in a closed conductor. Voltage can be induced in a closed conductor if the magnetic flux through that closed conductor is varying with respect to time. Then the voltage can be induced. So Faraday's law says the closed line integral of electric field intensity is equal to some voltage, and this voltage will depend on the change in the magnetic flux with respect to time. And there will be one minus sign, and this minus sign says that if the magnetic field is increasing, then the voltage, the produced voltage, will be in such a way that the current which flows in the conductor will oppose the change of this magnetic field. This negative sign explains the Lenz's law. Lenz's law. So what I mean, if there is a closed conductor, if there is a, suppose this is a galvanometer or any resistance, and this is a closed conductor, and there is some magnetic field, in this. So it is placed in some magnetic field. Cross means magnetic field is inside of the paper, right? So if you move this conductor, if you move this conductor, right now this magnetic field is static. There is no change of this magnetic field for this conductor. But if you move this conductor, suppose I am moving this conductor in this direction or in this direction, what is happening? The area is changing. So now this is the area of this conductor, right? When you move this conductor on the left side, the area changes. Area changes means what is the magnetic flux? Magnetic flux is given by magnetic flux density dot a, b dot a, or we can say b a cos theta. Theta is the angle between the magnetic flux and the plane, and a is the area. So now the area is changing. Area is changing means the magnetic flux is changing. So when the magnetic flux changing with respect to time, what will happen? Voltage will produce, we will produce. So this is the Maxwell second equation given by Faraday's law. Faraday's law says that voltage can be induced in a closed conductor. So this galvanometer, when you don't move this closed conductor, this galvanometer will show zero reading. But when you start moving this conductor here and there, what will happen? Area will change, then voltage will be producing. So this galvanometer will show a deflection. So this will be a positive reading if you are moving in this direction. If you are moving in the opposite direction, it will show a negative reading in the opposite direction. So magnitude will be will depend on the velocity by which we are moving this conductor here and there, and the direction of this conductor, movement of this conductor, will give the deflection of direction, right? So whether the positive voltage is induced or negative voltage is induced, it will depend on the direction of movement of the conductor. Whether the flux is increasing or the flux is decreasing, it will depend on that. So this is the Maxwell second equation, which required the modification, and the modification is there will be some voltage, and that voltage will depend on the flux. Similarly, flux is nothing but we can we'll write like this, BA, or we can also write flux is nothing but double integral B dot ds, right? B dot ds. So just you put this B dot ds in this equation, then we will get the closed integral of electric field intensity is nothing but equal to curl B by curl T ds. So this is Maxwell's second equation for time varying field. Next, we will study the Maxwell fourth equation, which required modification. Maxwell fourth equation, ampere circuital law. So when there is, suppose there is a capacitor is there, right? What is ampere circuital law? Ampere circuital law says the closed line integral of magnetic field intensity is equal to the current. It is equal to the current. Now this we have applied some AC, Vm cos omega t, and current will flow in this circuit. Current will flow in this circuit, but this circuit is not closed. This circuit is not closed because this is a parallel plate capacitor. This is a parallel plate capacitor. It means it is a air or any dielectric, right? Dielectric. It is not a conductor, so it is not closed. This circuit is not closed, but still the current is flowing. Still the current is flowing, right? So ampere circuital law was failed to explain this current. So Maxwell said that there is a modification required, and he said that there is another current that is known as displacement current. So Maxwell said that this closed line integral of magnetic field intensity is not only equal to I, that is a conductional current, but there is one another current that is known as displacement current, and this displacement current will flow in this dielectric. So this current is IC, this current is ID. The magnitude of IC will always be equal to ID, will always be equal to ID. So when IC is 0, in the dielectric, IC will be 0 and ID will be non-zero. In the conductor, IC will be non-zero, ID will be 0. So this is the Maxwell fourth equation. So now we will tell you this, what is the value of this displacement current. This is actually given by Faraday's law, or you can say equivalent to Faraday's law. Faraday's law says that the change in the magnetic flux, the change in the magnetic flux is a form of a voltage, right? It is a form of a voltage that we studied in the last equation. So in the fourth equation, this equation, so if the change of the magnetic flux can be a form of a voltage, then it says that the change in the electric flux, this is electric flux density, right? Electric flux density is a form of a current, is a form of a current. According to Faraday's law, if the change in the magnetic flux is equivalent to a voltage, then change in the electric flux is equivalent to a current. So ID is nothing but is equal to curl D by curl T. So ID is nothing but equal to curl D by curl T ds. So it is equal to this. So similar, so the equation will become H dot dl This IC is conductional current plus curl D by curl T ds. So this is the integral form of Maxwell equation. Similarly, you can calculate the differential form using you can apply just the Stokes theorem. If you apply the Stokes theorem, you'll get left hand side del cross H, right hand side JC, where JC is conductional current density sigma E. Its value is sigma E plus JD. JD is displacement current density. Its value is curl D by curl T. Similar to curl B by curl T that we studied in the third Maxwell second equation. Here it is a curl D by curl T. Similar to curl B by curl T, rate of change of magnetic flux density that we studied in the previous equation. Here we have a curl D by curl T. Right. So these are the four Maxwell equations for the time varying field. So what is the change? The change is only in the second equation and in the fourth equation. So one quantity will add in the second equation, that is curl B by curl T. If you see this differential equation, minus curl B by curl T, and if you see in this, there will be displacement current density will be added. So this is the Maxwell equations in for the time varying fields. So I will just discuss one question that was given in a GATE 2010. It's very simple question, GATE 2010 question. What was given? It is just related to the magnetic field direction. Suppose this is X, this is Z, this is Y, right? So suppose there is a one line, sorry, X Y Z. If you use your right hand thumb, right crossed finger, then this should be X. This should be X, right? This is X, Y, and then this will be Z. So suppose there is one current carrying wire is given. Current carrying wire is given in this parallel to Y, and one current carrying wire is parallel to X. Then the question was, calculate the magnetic field component at the origin. At the origin, how many magnetic field components are present at the origin? This was of 2 marks. So to calculate this, so you just need to find out the magnetic field components at the origin. How to calculate? You just need to apply the that formula that we studied in the previous lecture. We studied that how to calculate the magnetic field direction. The magnetic field direction is given by the direction of the current cross product with the direction of the current cross product with the radial direction from current to that point, right? This we studied in the last lecture. So in this question, you just need to apply the same formula. So at the origin, so what is the first we will calculate the magnetic field component at the origin due to this current wire. What is the direction of the current? The direction of the current is AY. What is the radial direction? Radial direction is minus AZ. Minus AZ, right? So what will be the magnetic field component at the origin due to this current line? AY cross minus AZ. It is equal to nothing but minus AX. So there will be one component of minus AX because of this line, infinite line. Now we'll calculate because of this line. This line. What is the direction of the current? AX. What is the direction of the radial direction from current to the origin? What is that? That is minus AY. Minus AY. So the direction of magnetic field will be given by equal to minus AZ. So these two components will be present at the horizon. So this is a very simple, just based on a small formula, the question was given, right? So it's very simple, just based on the concept. If you know the concept, you can give the answer very easily, right? So this is all about the Maxwell equations, right? In for a static field and the magnetic and the time varying field. So if the time, if in this equation, if in this Maxwell equation, time varying, suppose the magnetic flux is not varying with respect to time, so what will happen? So this factor will become 0 and this equation will reduce to the static field equation. Similarly, if the electric flux is not varying with respect to time, then this part will become zero and it will become the static equation. Closed integral of magnetic field intensity is equal to I, simply I. This factor will not be here. So this equation will reduce to the static field equation, right? Now we'll study the electromagnetic propagation, EM wave propagation. So when the EM wave propagates, how this EM wave propagates, how this EM wave propagates, that will actually depend on Maxwell's two equations that we just studied. So let me just write these two equations which are going to be very useful for EM wave equation propagation. So this is the one equation, or you can write, because we know B is equal to mu H. So this is the number one equation that is very useful. Del cross H is equal to curl D by curl T plus sigma E. Or we can write epsilon curl E by curl T plus sigma E. This is equation number two. So if you see EM wave propagation, what does it mean? Means electric field and magnetic field will sustain each other. Both the fields will exist. It is similar to LC oscillator. In LC oscillator, what happens? Kinetic energy converted into the potential energy converted into the kinetic energy, right? So these two energies transforms each other. Similar to that, in EM wave, when an EM wave propagates in free space, what happens? Electric field converts into magnetic field converts into electric field. How? Using these two equations. So we will see these two equations, how we are, see, suppose we have a magnetic field which is time varying. Suppose we have a magnetic field which is time varying. It is equal to del cross E. It means it will produce a space varying electric field, because del is nothing but space varying quantity, right? Del is a space varying quantity. So it will produce an electric field, right? Space varying electric field. And if this space varying electric field is also varying with respect to time, it means this, then what will happen? This will produce a space varying magnetic field, right? So what does it mean? So this magnetic field, if it is time varying, this will produce an electric field. If this electric field is time varying, it will produce a magnetic field, right? So what is happening? If this is electric field, it is producing a magnetic field. If then this is an electric field, then this is producing a magnetic field. So like this way, electric field will produce magnetic field will produce electric field, again electric field will produce magnetic field. So in this way the wave will propagate. So these two equations are very important, which governs the electromagnetic wave propagation, right? So E will produce H will produce E. So this way the electromagnetic wave will propagate. So there are actually so when EM wave propagates, there are some quantities, because see, when we apply in a network theorem, circuit theory, we have a V and I. So there is always a loss in the resistance, right? So this free space is also also a resistance for EM wave. So what is the resistance of that? That is given by the formula that is known as intrinsic impedance of the medium. Intrinsic impedance of the medium. Intrinsic impedance of the medium. Let me just share my notes. I will tell you the formula here. So first there these two equations are used for the EM wave propagation, right? So there we have one quantity, that is gamma. This quantity gamma, this gamma is known as propagation constant. This gamma is nothing but a propagation constant, and its value is given by j omega mu bracket sigma plus j omega epsilon. So this is a complex quantity, right? This is a complex quantity. So its value is equal to, it can be means decomposed into two components, the real part and the imaginary part. Whatever the real part we have, this real part is known as attenuation constant. Attenuation constant will tell you how, when the EM wave propagates through the medium, how much attenuation will be there, because an EM wave cannot go up to infinite distance, right? So when EM wave will propagate, there will be some attenuation. That attenuation will be given by alpha, and the phase constant beta, the imaginary part, will tell you the phase constant, how much phase is changing when the EM wave propagates. The propagation is, the propagation of the EM wave is mainly depends on the beta. If there is no phase constant, it means there is no phase change. When there is no phase change, in that case electromagnetic wave will not be able to propagate. So propagation is only possible because of this beta. And if alpha is equal to 0, it means there is no attenuation. It means there is no attenuation means the EM wave will propagate without any attenuation. The amplitude of the E wave and H wave will remain constant, right? So these two quantities are very important quantities, and their formula is given by this: alpha is equal to omega under root mu epsilon by 2 bracket under root 1 plus sigma upon omega epsilon square minus 1. And beta is also the same formula, only difference is here there is a minus sign, here it is a plus sign. Only difference is this one. So this difference is actually very important. So this we will discuss now. If you see, there is one quantity here of sigma upon omega epsilon, sigma upon omega epsilon, this quantity, right? If sigma upon omega epsilon, let me just explain you in this whiteboard. So we have alpha, which is equal to omega mu epsilon by 2 under root 1 plus sigma upon omega epsilon square plus 1, sorry, minus 1. Just a second. Here it is a minus 1, right? And similarly, we have a beta, omega mu epsilon by 2, 1 plus sigma omega epsilon square plus 1. So suppose sigma upon omega epsilon is much less than 1. If sigma upon omega epsilon is much less than 1, in that case we can neglect this factor with respect to 1, right? If we neglect this factor with respect to 1, then this quantity will be 1, right? This quantity will be 1, and 1 minus 1 0, so it will become 0, right? So it means there is no attenuation, right? No attenuation, no attenuation. And beta will be maximum, right? Beta will be maximum. But when sigma upon omega epsilon is much greater than 1, in that case we cannot neglect this. Then what will happen? There will be large attenuation, large attenuation, large attenuation, right? For this there will be no attenuation. So what is exactly sigma? Sigma is conductivity of the medium. So if the conductivity of the medium is very less, if it is not conductive, it means like a free space. Free space, the conductivity is 0, right? The conductivity is 0. In that case, there will be no attenuation. So electric field, EM wave can propagate easily. So EM wave can propagate in free space. But what happens in conductor? The conductor conductivity is very large, very large. So sigma upon omega epsilon will become very large, large quantity. So EM wave will attenuate, right? So EM wave will not be propagating in the conducting medium. So it is totally opposite to the VI waves. What happens in VI? VI totally depends on the conductivity of the medium. If the conductivity is more, If the conductivity is more, then this will propagate. The current will be very good, very large, right? If the conductivity is of a medium is very good, then VI wave will propagate. But if the conductivity is very high, then EM wave will not propagate. So EM wave is totally opposite to the VI waves. If there is a conductor, then VI wave are there. If there is a non-conductor, free space, dielectric, then EM wave will propagate, right? So this quantity sigma upon omega epsilon not only depends on sigma. This also depends on omega. This also depends on epsilon. Suppose for a constant value of sigma and epsilon, it depends on the frequency. Frequency. What is frequency of operation? So it means I will just give you one example. For your body, human body, the conductivity is fixed, right? The conductivity of your body is fixed, epsilon is fixed, right? We cannot change these two things. These two things are fixed. What is the main important thing is omega. So light has frequency around like this, 10 to power 14 15 hertz, like that, right? But x-rays have a frequency of around 20 to power 22 hertz or 24 hertz, something like that, right? So light cannot penetrate through your body because the frequency is less. It means sigma upon omega epsilon factor is much greater than 1, much greater than 1, because frequency is less, right? But for x-ray, omega is very high. Omega is very high means if omega is high, this factor will become less. It becomes less than 1. So EM wave can propagate, because light and X-ray, these are nothing but the EM waves, right? Electromagnetic waves. So light cannot penetrate through your body, but X-ray can penetrate through your body. So it depends on sigma upon omega epsilon factor, right? So basically it depends on the frequency for a fixed medium. If the medium is fixed, it will depend on the frequency of operation. So that's why X-ray is done to analyze the body parts, what is happening inside, right? So we don't use the simple light. Light has a less frequency, cannot penetrate through your body, but X-ray can penetrate. It depends on this alpha, right? Alpha. So alpha depends on sigma upon omega epsilon. So suppose now we'll just discuss about the EM wave equation, EM wave equation. Before that, just let me tell you one thing in the intrinsic impedance, about the intrinsic impedance. So this is the formula for the intrinsic impedance. This intrinsic impedance is similar to the resistance or impedance in the network theory. We have a Z, right? We have a Z that is equal to R plus JX. Similar to that, we have impedance of the medium. So when EM wave propagate through a medium is also has some impedance for EM wave. That impedance is the intrinsic impedance, and that is given by E upon H. E upon H. It is similar to, E is nothing but similar to V. H is similar to I, right? So V upon I. V upon I is nothing but a Z, right? So here we have V upon I, and this formula gives you the intrinsic impedance. It again the unit is ohm because it is an impedance. And for the free space, if you put the quantity, sigma will become 0, because for the free space sigma is equal to 0. Epsilon will become epsilon naught, mu will become mu naught. So the if you put all the values, mu naught, sigma, epsilon on, we will get the impedance of the free space is equal to 120 pi, 120 pi or 377 ohm. So this is the impedance of the free space, right? So so this is all about the EM wave. So suppose now I will just discuss one example. Let me just discuss one example with you, so that before that, let me just discuss one thing where we have yeah, EM wave propagation in a good conductor. This is very important. You will see a question on this definitely. In a good conductor, so we have a gamma, this in a good conductor sigma will be very large, so sigma upon omega epsilon will be very large. So if you just apply this condition and calculate the value of alpha and beta will be equal. alpha equal to beta equal to this value under root pi f sigma mu, right? And alpha is what? Alpha is nothing but the attenuation constant. Alpha is nothing but the attenuation constant. So if you see the equation of EM wave, if you see the equation of an EM wave, the equation of an EM wave is given by very simple equation. It is not written here. Just let me write in the whiteboard. So the equation of an EM wave is given by E equal to E naught e to power j omega t e to power minus gamma z, where this is our time harmonic source and this is a gamma is just a propagation constant with respect to z, right? So if you put the value, it is equal to e to power j omega t e to power minus, sorry, we just need to put the value of this alpha plus beta j beta z equal to e naught minus alpha z e to power j omega t minus beta z. So this is the phase part. This is the phase part. And this is the magnitude. This is the magnitude part, right? This is the magnitude part. So this magnitude, if you see, is decreasing with respect to z. If you increase the value of z, z is the direction of propagation. We are assuming a uniform plane wave where the E is given by this. Is it a very important property of a uniform plane wave is the direction of propagation is given by this E cross H, the direction of E, the direction of H, then the direction of propagation. So our electric field direction is AX, then the magnetic field direction will be AY because the direction of propagation is AZ. So this will always follow the right hand sequence rule. E cross H is equal to P. P is the direction of propagation. Similarly, H cross P is equal to E. Similarly, you can say P cross E will be equal to H. It will always follow the right hand rule like this formula, right? This is the property of a EM wave, a uniform plane wave. So if you see this magnitude, magnitude is decreasing with respect to Z as we are going. Suppose this is a conductor. Suppose this is the source. This is the conductor. This is the conductor in the direction of Z. So as the electric, suppose this is our electric field. So as we are moving, the magnitude of the electric field will start decreasing because the magnitude is given by e to power minus alpha z. And in the conductor, alpha is very, very large quantity, right? In the free space, alpha is equal to 0. So if alpha is equal to 0, this will become E naught. So the if you see in the EM wave in the free space, it will be like this. There will be no change in the amplitude. Amplitude will remain constant. But in the conductor, the amplitude will start decreasing exponentially. Exponentially. So it will start decreasing exponentially. So there is one quantity that is known as skin depth. Skin depth. Skin depth. Skin depth is denoted by delta. Delta. And it is given by 1 upon alpha. It is the distance, skin depth is the distance covered by EM wave in the medium when when the electric field magnitude reduces to 36% or you can 36.7% of the maximum value, because we know E is nothing but equal to E naught e to power alpha z. Sorry, E naught alpha z. When z is equal to 1 upon alpha, when z is equal to 1 upon alpha, what will happen? E naught e to power minus 1 e naught upon e. E is nothing but 2.3 something, and if you see, it will be nothing but 36%, something like that, right? So this is known as skin depth. It's very important. Skin depth. So skin depth is what? The distance traveled by a wave where the amplitude decays to 37% or 36.7% of the original value. That distance is known as skin depth. So what is the value of this alpha for a conductor? If you see in the formula, this is the, because we know alpha. What is alpha? Alpha is this formula, right? So 1 upon alpha is, that is skin depth. So skin depth is given by this formula. This is the skin depth. Delta, it is equal to 1 upon alpha, it is equal to 1 upon under root pi f sigma mu. It is very important. You may get this question. You just need to you will be having all the quantities. You will be having mu. Mu is nothing but 4 pi into 10 to power minus 7. Sigma will be given to you, the conductivity of the medium. The frequency of operation will be given to you. Pi, you already know the value, 3.14. You just need to apply these three quantities in this formula. You will get the value of skin depth. And the unit will be, that depends on the meter or centimeter. That will depend on the values given to you. So this is known as skin depth. And similar to this, we have a skin resistance, which is given by this formula. Skin resistance r under root, this is nothing but you can just need, you just equate this skin depth equal to 1 upon sigma rs. From here you can calculate the value of rs. Rs is nothing but a skin resistance. Skin resistance. So what is happening basically? Basically it happening that the electromagnetic wave is traveling in the free space without attenuation. But when it comes to the conductor, the attenuation constant alpha becomes large. So because of that, electromagnetic wave is not able to propagate. So VI wave will propagate, right? So this is all about electromagnetic waves. So I will just discuss one question. Suppose, let me just discuss one question with you. Suppose we have E, electric field is given that EP e to power j omega t minus 280 pi y a z. And similarly we have H, 3 e to power j omega t. This is a GATE 2011 question. 80 pi y a x. Sorry, a z ax, right? So what is given to you? And frequency is also given to you. Frequency is given as 14 into 10 to power 4 hertz. And beta is see, beta we need to actually calculate from the given question. So this is given to you. Epsilon r is mu r is given as a 1. Epsilon r need to be calculated. Epsilon r need to be calculated. Eta also need to be calculated. So various quantities that you need to calculate. And the velocity also you need to calculate, the velocity of the electromagnetic wave. So first you need to equate this equation with our general equation. What is the general equation? The general equation says that minus alpha z e to power j omega t minus beta z ax, right? But the equation given in terms of y and az, so you just need to remove here y, here z, right? So what is the direction of the propagation? The direction of propagation always given by this quantity, whatever is given with respect to beta. This is nothing but our beta. This is nothing but our beta, 280 pi. And this is nothing but the direction of propagation. This is the direction of propagation. This is beta. Omega t is as it is, right? What is alpha? And if you compare, EP is nothing but equal to E naught alpha z. It means alpha is nothing but equal to 0, because there is no exponential term here. There is no exponential term. It means alpha equal to 0. It means alpha is equal to 0. So you calculated alpha, you calculated beta. Beta is given by 2 pi by lambda. This is the formula for beta. What is beta? Beta is phase shift constant. Phase change per unit length. Phase change per unit distance. Distance is lambda. Lambda is a wavelength. When a wavelength is changed, then the phase shift will be 2 pi. So from here we can calculate the value of lambda. Lambda is nothing but 140, 1 upon 140. So now we will calculate the value of uh, because we know the speed velocity, phase velocity is nothing but lambda into frequency. This is a very simple formula. So and this is also given by the this velocity of light divided by the dielectric constant. This is the formula for the phase velocity in any dielectric. The velocity of light divided by root epsilon r. So lambda is given, frequency is given. You can calculate the value of epsilon r. So if you calculate the value of epsilon r, it will be equal to 9. So once you calculate the value of epsilon r, you can apply in eta. Eta is nothing but j omega mu naught mu sigma plus j omega epsilon. See, sigma is 0. See, sigma is 0, right? Because attenuation is 0, sigma 0. So it is nothing but equal to mu naught upon naught epsilon r, right? It is nothing but 120 pi divided by root epsilon r. It is nothing but 377 divided by 3. So it is nothing but 40 pi, or you can say whatever the value is, you can write here, right? So this way, so so this way we calculate all the values. Now the question is, what is the value of EP? What is the value of EP? Because we know eta is nothing but equal to E upon H, right? So what is E? E is nothing but eta into H, eta into H, right? So what is E? We know the value of HP, right? Because EP is equal to eta HP. So we know the value of eta, we know the value of HP. Just calculate the value of EP. EP is nothing but 40 pi into 3 is equal to 120 pi. So in this way, we calculate all the constants, all the unknown values, right? So you just need to compare with the general equation. This is our general equation. This is our general equation. This is the direction of propagation. This is the, so what will be the direction of propagation? You can calculate from here also. E cross H, E cross H, A Z cross A X. What is that? A Y, and that is given. This is Y. If this was not given, you can calculate this using these two values, right? Just making it cross product. Next, I will discuss the pointing theorem. In the pointing theorem is, I will not go into the detail. I will just tell you why we use this theorem. This theorem is used to calculate the power density, or this is pointing theorem is nothing but a power density calculation E cross H. So whenever we want to calculate the average power, what we will do, the average power for a wave which is propagating in the z direction will always be given by the RMS value, multiplication of RMS values. So if E RMS is E max by root 2, E max, because RMS value of any exponential, complex exponential sinusoidal signal is given by maximum value divided by root 2. So similarly for this, E H max by root 2. So it is nothing but E max H max, right? What is E max? E is given by E naught e to power minus alpha z e to power j omega t minus beta z. What is the maximum amplitude? This is the maximum amplitude. So similarly, H naught e to power minus alpha z. You just need to put in this equation. If you put, then you will get 1 upon E naught H naught e to power minus 2 alpha z. It will become 2 alpha z, because alpha z come from here, alpha z will come from here, right? So we will get, this will become, so if you put this eta is equal to E upon H, then you can write E is nothing but eta into H, right? Eta into H, eta into naught H, right? Like that. E naught is equal to eta into H naught. So if you write, you can write it in terms of H naught square also. or you can also write in terms of E naught square. So these are the two formulas that you can use to calculate the average power. These are just the formulas you use to calculate the average power. So these are the two formulas can be used for calculating the average power, right? So next topic is very important. Sometimes question comes from that topic, that is a wave polarization. Wave polarization. It's very important and very easy. Nothing to do. You just need to understand the concept. Wave polarization. What is the polarization? The polarization is the basically the orientation, the relative orientation of electric field. Relative orientation of electric field. Simply, that is known as a polarization of the wave. Suppose we have an equation E is equal to E naught sine omega t minus beta z ax. Don't confuse with the sine word. It is just the imaginary part of that. Omega t minus beta z, nothing else. It is equal to cos. You may see cos or you may see sine in the equation. Don't confuse with that. These both things are same. So suppose this is given to you, and the question is, what is the polarization of the wave? The polarization of the wave is same as the direction of electric field. So what is the polarization of the wave? X direction. X direction is the polarization of the wave. X direction is always considered as a horizontal polarization, horizontal, and Y direction is considered as a vertical. So it is a horizontal polarized wave, horizontal polarized wave. Suppose instead of AX, AY is given, AY is given, then it is a vertical polarized wave, vertical polarized wave. But there also one definition, the polarization is divided into three types. One is linear, second is circular, and third is elliptical. And actually this elliptical is the general polarization. These two, linear and circular, are the special case of elliptical. But we will discuss one by one. First we will discuss linear. What is linear? Linear is when there is only either this is the case of a linear. Actually this is the case one, which is a linear. Linear horizontal polarized, linear horizontal polarized, linear vertical polarized, linear vertical polarized. So how to draw this? So how to draw this? We can say like this. Suppose this is y, this axis is x, then z will be outward, right? Z will be outward, z will be outward. So you just whatever the equation given to you, you just need to put t equal to 0. First put take xy plane. Xy plane means z is equal to 0, right? Xy plane is z is equal to 0. So you can remove this portion. You can forget about it. While calculating the polarization, you forget about the z part, this phase part, this z part, right? Space part. You need to only assume the time part, this. And now put t is equal to 0. If you put t is equal to 0, electric field will become 0. This point will you get, right? Now you put t is equal to pi by 4. T is equal to pi by 4 means omega t is equal to 90 degree. If you put t is equal to pi by 4, you will get maximum value is equal to E naught. So it means as you move from t is equal to 0 to t is equal to pi by 4, what is happening? Now you will get the value here. Electric field will be this in the x direction. So it means electric field is increasing in this direction, right? So now you put t is equal to pi. T is equal to pi. T is equal to pi means nothing but equal to 180 degree, right? 180 degree. Sine 180 degree means 0. So you are coming back. You are coming back at this point, right? So now you put t is equal to 3 pi by 4. If you put 3 pi by 4, you will get minus e, minus e. So it means you are increasing in the negative half, negative x direction. Now you put t is equal to 2 pi. You will come again at this point. So what is happening? Electric field is only in a particular direction. It is only in a particular direction, and the direction is x-axis. So it means this wave is polarized in x direction, and x means horizontal. It is horizontal polarized. Instead of ax, suppose ay is given, then the plot will be like this, right? The plot will be like this. Then it is known as vertical polarized. And this both of case these are the case of linear wave polarization, right? Linear. So there is one more case, case 3, which says that the electric field given electric field has two components. This, suppose the electric field is given like this, plus this. So if you see, there are two components. So what is the polarization of the wave? So first, to find out the polarization of the wave, you just put a z equal to 0. You just remove this portion. You remove this portion, right? Now put now put now put t is equal to 0. If you put t is equal to 0, this component, first component, this component is 1, this component is 2, this component and this component, both the components will be 0. So we'll get this point, right? You will get this point. Now put t is equal to pi by 4. If you put pi by 4, this component will become e x naught by root 2. This component will become e y naught by root 2. So you will get like this, right? So this is, suppose this is e uh, sorry, pi by 8, for a pi by 8. If you so you will get this in the x direction, this component, y direction in this component, the net value will be this, the net value will be this, right? Similarly, you put 90 degree in this, you put 90 degree, 90 degree, right? 90 degree. So if you put 90 degree, this will become e x naught, this will become e y naught, this is e x naught, this is e y naught, and the magnitude will be the this this will be the magnitude. So what is happening, as the t increasing, we are moving in this direction, we are moving in this direction, right? So now t further increase the t, you will see, you will be coming back in this direction, you will be coming back in this direction, and will further go in this side up to this. And when you again put t is equal to 2 pi, you will come again at this direction, and you will be at this. So if you see, this is again in the particular direction, straight line, right? This is again a straight line. So this is also a linear polarized wave. This is a linear polarized wave. This is neither horizontal polarized nor vertical polarized. It is simply a linearly polarized wave. So this is also the case of a linear polarization when there are two components are given, right? So this is the case when there is, so there are three cases: when either the first component is given, then it is linear; when either the second component is given, then it is also linear; when both the components are given but there is no phase difference between these two components. So if you see, there is no phase difference between these components. This is also sine omega t, this is also sine omega t. Next case we will discuss the circular polarization case. So for this case, case 4, suppose E is given as E naught sine omega t minus beta z Ax plus E naught cos omega t minus beta z Ay. So if you see, there is a phase difference. Here it is sine, here it is cos. So there is a phase difference of 90 degree. There is a phase difference of 90 degree. So if you now plot these in z is equal to 0 plane, and we are assuming the amplitude of both these are equal, E naught. So what is at t is equal to 0? At t is equal to 0, the first factor will be 0, the second factor will be maximum E naught, and the direction will be E. So at t is equal to 0, we will get E 0 ax plus E naught ay, right? So it means we are getting this value at t is equal to 0. This is at t equal to 0, right? Similarly, put t is equal to omega t is equal to pi by 4. Pi by 4. If you put pi by 4, you will get E naught by root 2 ax plus E naught by root 2 ay. So E naught by, suppose this is E naught, then E naught by root 2 is this. E naught by root 2 is this. Suppose this is E naught. Then at t is equal to pi by 4, we will get this point. So this point is t is equal to t by 8, or omega t is equal to pi by 4, right? Similarly, put t is equal to t by 4, t by 4, capital T by 4, or you say omega t is equal to pi by 2, 90 degree, 90 degree. If you put 90 degree, this will become maximum first, this will become minimum 0. So what you will get? We will get E equal to E naught ax plus 0 ay. So ay component will be 0, ax component will be maximum. So we will get this point. So this point is t is equal to t by 4, or omega t is equal to pi by 2. Similarly, you increase the value of, so as you are increasing, what is happening? You are moving from this point to this point, then this point, and further if you increase, you will move like this. You will move like this, like this, like this, like this. So at t is equal to 2 pi, sorry, at t is equal to pi, you will reach here. At t is equal, omega t, sorry, omega t is equal to 3 pi by 2, you will reach here. At t is equal to 2 pi, you will reach here. And all the values are at equidistance from the origin. So it is the form of a circle, right? So what is the polarization of the wave? The polarization wave is circular, circular. So in circular polarization also, in circular polarization, we have whether it is left hand circularly polarized, left hand circular polarized, or right hand circular polarized. So it is also divided into two parts, whether it is a left hand circularly polarized or right hand circularly polarized. It's very simple. If your right hand thumb points towards the propagation direction, you need to listen this very carefully. If your right hand thumb points towards the direction of propagation, so what is the direction of propagation? Z. This is the direction of propagation, right? So the direction of propagation is this one, outward, right? So now you put your right hand thumb towards the Z direction, and if your crossed fingers, are following the value of this circular motion, then it means your uh, wave is right hand circularly polarized. Is this following? If you use your right hand and put your thumb towards the direction of outward, then the crossed fingers will oppose the direction of this circular motion, right? Because our if you use your right hand, your fingers will be in the anti-clockwise direction, right? So it is not satisfying. Now you use your left hand. And use the thumb in the direction of outward, in the direction of propagation, and see whether your crossed fingers are satisfying, are matching with the circular motion. Yes, because your left hand is in clockwise and this is also in clockwise direction. So it means this wave is left hand circularly polarized wave. This wave is left hand circularly polarized wave, right? Suppose this is Z propagation direction, and as the time advances and our polarization is like this, it is moving in this direction, then this is a right hand circularly polarized wave. This is right hand circular, but this is left hand circularly polarized wave. This is left hand circularly polarized. I will give you one more example. Suppose this is X, this is Y, and this is our Z, right? But our direction of propagation is minus Z. Suppose the direction of propagation is minus Z. It means the direction of propagation is inward. Inward. It is not outward, it is inward, right? And if you plot the this whatever after varying the time, suppose this is at t is equal to 0, this is at t is equal to t by 4, this is at t by 2, this is at 3t by 2, sorry 3t by 4, this is at t is equal to capital T. So if you do like this, right? So now the motion is in clockwise direction, right? Motion is in clockwise direction. But what is the direction of propagation? The direction of propagation is inward. So if you use your left hand and point your thumb inward, then the crossed fingers will be anti-clockwise. So this is no more left hand circularly polarized. This is not a left hand circularly polarized, right? It is a right hand circularly polarized. If you use your right hand and point your thumb towards the direction of minus Z inward inside the paper, then the crossed fingers will be in the clockwise direction. It means it is satisfying, right? So our right hand is satisfying. Right hand is satisfying means this wave is right hand circularly polarized wave. So this wave is right hand circularly polarized wave. So whether it is a right hand or left hand, it will not only depend on this advancing time, whether it is a clockwise or anti-clockwise. It will also depend on the direction of propagation, right? It will also depend on the direction of propagation. So these are the two cases, linear and circular. Next we'll see elliptical. Elliptical is very simple. So suppose E is equal to E x naught sine omega t minus beta z ax plus ey naught cos omega t minus beta z ay. So it is very similar to the previous circular polarization equation, right? But only difference here is magnitudes are not equal. Magnitudes are not equal. There we assume the magnitude are equal. Magnitudes are equal. So if you plot this, you will see like this. Either you will see like this or you will see like this. I am not able to plot it very, you can see, just see it should be like this actually. Anyways, I just wanted to explain that this is elliptical, right? So this is elliptical. So this is elliptical. Whether it is a left hand elliptical polarized or right hand, that you can manage using the right hand thumb rule, right? Or left hand thumb rule. If left hand is satisfying the thumb rule, then it means left hand circularly polarized. If the right hand is satisfying, it means the right hand circularly polarized wave, right? So this is the elliptical polarized. So here actually why the linear and the circular polarized are the special cases, because this is, if you assume this is a minor axis, this is equal to E y naught, this is equal to E x naught. There is one term that is known as a axial ratio. Axial ratio. Axial ratio is the ratio of major axis to the minor axis, so any axis, whatever. So if the axial ratio is 1, if the axial ratio is 1, that means both the values are equal. If both the values are equal, it means it is nothing but a circular polarized case, right? Means it is a circular polarized case. And if the axial ratio is infinity, if the axial ratio is infinity, it means the minor axis is 0. Minor axis is 0 means either this component is 0 or this component 0. It means only one component is present, then it means it is a linear polarized. It is a linear polarized. So that's why I say that this circularly polarization and the linear polarization are the special case of the elliptical. When axial ratio will become 1, it will be circular. When axial ratio will be infinity, then it will be linear. When it will be between 1 and infinity, then then it is a elliptical polarized, right? So this is very simple, the wave polarization, very simple. And you may say this type of questions in the gate. You just need to find out whether it is which polarized wave, whether it is linear, circular, or elliptical. So in case of any doubts, you can ask me now, and I will be sharing the notes with the madam will circulate the notes to you. So now you can let me know if you have any doubts. In the next lecture on Monday, we will discuss about the transmission lines, waveguides, antennas, a little bit about radar and optical fiber communication.
Yes. Anybody?
No doubt, sir.
Anybody is having doubts?
No, ma'am.
Hmm. Thank you so much, sir.
Thank you, ma'am.
Thank you, sir. Sir,
Oh,
Monday is the next session is on Monday.
yes, yes, at 11:30 we'll meet on Monday. Yes,
Okay,
thank
sir.
you.
Okay. Thank you so
Okay.
much, sir. Thank you. हेलो, आवाज जा रही है सभी को?
Yes, ma'am.
ठीक है. नेक्स्ट सेशन विल बी ऑन मंडे.
Okay, ma'am.